Okay, we just talked about, we've already talked about oxidations of alcohols. How can we increase the number of CO bonds? We can also do reductions of alcohols. So a reduction means we're going to decrease the number of CO bonds while increasing the number of CH bonds. That's the opposite of an oxidation. And so an alcohol has just one CO bond. So in order to reduce it, you'd be going to replacing with a hydrogen. So you'd be going from an alcohol to an alkane. We would describe that as a reduction of an alcohol. And there's a few strategies we can do for this. One of them is via an SN2 mechanism with hydride. Hydride is H minus. And if we had a source of hydride, then it can do an SN2 mechanism. But what's the problem with just using the alcohol? The source of hydride we had that was nucleophilic was something like lithium aluminum hydride. Lithium aluminum hydride, LiAlH4. That was a source of hydride. What would happen if I mixed an alcohol and lithium aluminum hydride? Well, I wouldn't expect to do an SN2 mechanism because, once again, my OH is a poor leaving group. But in this case, it's not that there's no reaction because the hydride, just like a Grignard, is an extremely strong base. And the alcohols, remember, have a very acidic proton. That's one of the properties of alcohols. So, in fact, this would react to give an O minus. It would deprotonate, and you would get some hydrogen gas being formed, and you would form the lithium salt here, or the aluminum salt of the O minus of the oxygen. And so this is fine if you want to deprotonate. You could use LAH to deprotonate an alcohol, but you couldn't use it to do a substitution. So instead, here's another case where if we instead made the tosylate, tosyl chloride and pyridine, replaces the OH with an OTS. Now that we have a good leaving group, LAH, lithium aluminum hydride, can do an SN2. This is a great nucleophile. Remember, we put little quotes around it because it is always coordinated with the aluminum. That's the nucleophilic hydride that we have, and it will, in fact, do an SN2. And that would be a way of replacing a leaving group with a hydrogen, in this case a tosylate with a hydrogen. So overall, our transformation has been to reduce the alcohol. Okay, just a little note here. Another source of hydride we've seen, especially with alcohols, is sodium hydride. We use this as a base, and in general, because this is ionic, because this is more reactive, this is prefers to act as a base rather than a nucleophile. Okay, so when you're thinking hydride, that's a good distinction to make, is that when you want a nucleophilic hydride, we use sodium borohydride or lithium aluminum hydride, and NaH you should consider just as a base. Anytime we want to deprotonate something, NaH would be a good choice there. Okay, another strategy is to think about, maybe if we do a retrosynthesis here, and we consider what reactions have we ever seen that give alkanes as products. That's kind of a strange reaction because there's no functional groups here. There's nothing left. Okay, well, what if we had an alkene in this position? Have we ever seen the conversion of an alkene to an alkane? Looks like we've broken the pi bond. We've added something to each carbon. What did we add? We added a hydrogen, and of course there's a hydrogen here too. This was a CH2, and now it's a CH3. So we could do catalytic hydrogenation. If we had an alkene, we could do a catalytic hydrogenation to give an alkane product. And what's nice about this is we've also seen alkenes as something that can be prepared from alcohols. Now, what does that reaction look like? What reagents will cause that transformation? We are doing an elimination. We're eliminating an OH, but we're also eliminating a hydrogen on the neighboring carbon, the beta carbon. So we're losing a molecule of water. We call that dehydration. And what reaction conditions do we need to dehydrate an alcohol? It's going to be some heat, very strong acid. So something like H2SO4, heat, strong, concentrated acid is what we need to do a dehydration. And so this would be a way of forming an alkene. Now remember, dehydration, we can have our alkenes move around, we could have we could have hydride shifts and such to get more stable carbocations. And so it's possible that our double bond might move around, but that's okay in this case because hydrogenation is going to get rid of the double bond in the end anyway. So we don't care so much where the double bond ends up here, but we do want to make sure that our carbocation is not something that can have a carbon chain rearrangement, because then that is not going to give us the alkane structure that matches the alcohol structure. So the dehydration is only going to work if there's no rearrangement of the carbon frame, of the carbon skeleton. Okay, and if that's the case, then this is another a great way to do the transformation is dehydration followed by reduction. Okay, so as you can see, reduction is not going to be something, there's no one magic reagent that's going to reduce an OH and replace with a hydrogen. We have to do some kind of multi-step transformation, either turning it into a good leaving group or getting rid of the oxygen first as a molecule of water, and then doing a complete reduction of both of these carbons via catalytic hydrogenation. Another